All right, and we're back. And you know what's interesting about that previous problem? This is sometimes you notice things in all of your stupidity. You know that at this step right here, I could have just canceled this 3 and this 3. I'm sure. Or at this step right here, I could have just divided 48 by 3 and got 16. And I know at least half of you were thinking, what an idiot. But that's okay, because I wasn't really paying attention. I was more or less worried that my new pencil, this little stylus, was working correctly. So, all right. So my apologies. Could have made that a lot simpler. But everything that we did is, okay, of course, correct. Now we need to go to our next problem, and you can imagine. I mean, just like in you know how math teachers like to proceed. We first give you a few easy problems to build up your confidence, and then next thing you know, we give you a whole bunch of hard problems, and now your confidence just withers away. So at least that's how it was for me going through school. So, but no worries. The process is the same. All right. So let's begin. So it says an airplane is flying on a path that will take it directly over a radar tracking station, right? So, in other words, eventually this airplane right here will fly directly over this tracking station. Now, it says the distance, S. Now, hold on. What is S? So notice that S here is the distance from the tracking station to the airplane, right? Now, of course, it makes sense. As that airplane it continues in its flight path, S should be decreasing, right? The distance from the plane to the tracking station should be decreasing and decreasing and decreasing until it is directly above the tracking station. And then as it continues, the S will start to grow again. So back to what I was reading, the distance S is decreasing at a rate of 400 miles per hour. But this is important. When S is equal to 10. All right, so what I need to do right now is I need to start collecting information. All right, so S, my apologies here. So S is what? S is the distance in miles from, I'm just going to put, of course it's of the airplane, so I'll just put to tracking station. All right, so S is the distance from the plane to the tracking station, measured in miles. All right. Now we know, let me continue to read. All right, and so I can start to collect more variables. The real point of this problem is to answer the question, what is the speed of the plane? Now, it's having a background in physics is not a requirement for this class, although I'm sure many of you have either studied physics or are maybe even currently taking physics. But the way you have to think about the perspective here, right? The point of reference is if you're measuring the rate of change of the airplane to the ground, or to the tracking station, or to, so depending on the reference point, will determine what the speed of the plane is, right? I mean, so we to ask how fast are you going, or what's the speed, is really an ill-defined question, because you really need to ask in reference to what? Well, let me kind of come back to that point. So now I'm going to read this little caveat right here. If it was, yeah, so let me read this. So an airplane is flying at an altitude of 6 miles, s miles from the station. So we know the altitude is 6, right? So we know the altitude of the airplane is 6 miles. And we know that the hypotenuse, so you can kind of see that a triangle is being formed here. So the hypotenuse of this right triangle is the distance from the plane to the tracking station. Now they're using x to represent the distance, or well, let's just make it some. The x is the other side of this triangle. Now, what we want is, we have to start to consider a few different things. We can define x as, say, some type of the horizontal distance to the tracking station. If you'd like, I can write that. So x is the horizontal distance. Again, it's going to be measured in miles to tracking station. All right, so we have two variables, x and s. So as this airplane continues on this trajectory, let's you and I agree that x is decreasing and s is decreasing, right? As that plane continues, x gets smaller, s gets smaller. Now, the first question that we need to address is how is it that we're going to relate these variables? Well, the picture is quite telling, right? I mean, it's the right triangle is already drawn. So we immediately know that we're going to be using Pythagorean's theorem in this problem. So let me go ahead and write the relationship here. So the hypotenuse, which is s squared, that's a horrible looking s, is going to be equal to the sum of each side squared. Each leg, I should say, squared. All right. So that's our relationship. There we go. Now, if I have two variables, I have an s and I have an x. If I'm going to take a derivative with respect to time, then now let's you and I agree that at some point in time in this problem, we're going to have a ds, dt, and we're going to have a dx, dt. Okay. So the way I'm going to approach this is, been doing this long enough. I know what I would do first in this problem. But let me just approach it the way I think a student might approach it, and then run into a common problem, and then how do we backtrack our way through it? Ready? So once I have the equation, if I'm a Calc 1 student, I'm ready to take a derivative, right? So when in doubt in a calculus class, a Calc 1 class, take a derivative. So let's go ahead and take these derivatives. So the derivative of s squared with respect to t, well, the derivative of x squared is 2x. So the derivative of s squared is, of course, 2. My apologies, that is too ugly. So the derivative of s squared is going to be 2s, what? Well, ds dt. Now that's going to be equal to, no, okay, if you take the derivative of x squared, isn't it just 2x? Right? Can't I just continue? Well, of course, it's 2x. If you were taking the derivative with respect to x, but you're taking the derivative with respect to t. So it's 2x dx dt. I don't know how to explain that any differently. If the variable that you're, look, if this variable right here is not the same as the variable you're in here, then you have to attach this dx dt ds dt. All right. Now, at this stage, if you don't mind, let me come down a little bit, rewrite this so it's not so sloppy. I'm going to give myself some more space. So we have 2 times s times ds dt, and that is equal to 2 times x times dx dt. All right. Now, the way this works is at some point in time, we better have some information to plug in, and we better know what it is that we are solving for, okay? So back to what I was saying a second ago. So they tell us, right in the beginning, that the distance of s is decreasing at a rate of 400 miles per hour. All right, a rate, meaning a rate of change. So let me go ahead and write 400 miles per hour for ds dt. Now, I'm going to make this 400 negative in just a second, and I'd want to make sure you know what word in that sentence tells us to use a negative. But ds dt is the rate that we were given. So 400 miles per hour. Now, I'm going to make this negative, and if the reason why it's negative is because it says it's decreasing. The distance is decreasing at a rate of 400 miles per hour, right? Back to that drawing, that picture, all right, as that plane continues towards that tracking station, S is decreasing. So we're going to, again, since we traditionally think of positive numbers moving this direction and negative numbers moving this direction, since it's decreasing, we're going to go ahead and label this negative 400 miles per hour. Now, it's not going to matter in the end, and you'll see why. But so that means, and let's get back to the question. It says, when S is equal to 10. So in this case, we also know that S is equal to 10 miles. So what do we need for this equation? So clearly, we are solving for dx dt, right? We already know ds dt. So clearly this is what we want to solve for. Now, that's great, but if you want to solve for dx dt, then you're going to need what? Well, you're going to need to know what S is, but that's okay. I know what S is. You're going to need to know what ds dt is, but that's okay. I know what ds dt is. And you're going to need to know what x is. But wait a minute, I don't know that yet. So I said just a second ago, I'm going to solve this the way I think a student would. Not the way I would have done it, but I've been training a lot longer. So now we have to go back and figure out what information do we have that we can use to solve for x. Well, let's draw this triangle. So we know that this side is 6, this side is x, and this side is s. Well, if you give me 2 of the 3 sides of a right triangle, I can solve for the third. That's no problem. Do they give us a second side? Well, they do. They tell us that s is equal to 10. All right. Now that means something. So now I actually, if I know that s is 10, then I can solve for x. Okay? So obviously, I'll just go through this quickly. So we have 6 squared plus x squared is equal to, well, now it's 10 squared. Let me go ahead and finish that up. So that would be 36 and 100. And we got to take the square root of both sides. So x is going to be equal to, let's see here, 100 minus 36, which is 64. So that's 8 miles. All right, ready? This guy now can go here with things that we know. All right. So I have everything that I need to solve for dx dt. The only thing left to do in this problem is to plug in all of this information that we have collected. So I'm going to do that, and I want to address something that I know one of you has thought of right now. So I want to address the question of why not plug in for s before you take the derivative, right? In other words, why not put a 10 here right from the beginning? And I'll address that question after I finish this problem. Ready? So let's go. So let's start plugging in. So 2 times, let's put a 10 here. And times, let's put a negative 400 here, is equal to 2 times, well, let's put a 8 here. And we want to be able to find dx dt. So no problem. That's, oh, what just happened there? Okay. So no problem at all. So that's going to be, so we got 16, we have, so that should be dx dt is equal to negative 500. Wish I had a calculator in front of me, but I think that's right. So negative 500, and of course, that's in miles per hour, right? Okay. So let me I'm going to come back in just a second and address this negative symbol in response to speed. But as of now, let me address that question of why not plug in the 10 right from the beginning. So I want to make sure you understand the question that let's assume for a second that somebody asked you for help in this problem. And maybe somebody asked, well, why can't you do the following right from the beginning? So if we know that s is equal to 10, imagine someone asking you, why can't I plug in a 10 right now? And then take a derivative. Well, because you could, but you would not answer the question you're seeking to answer, right? The derivative of 100 is obviously 0. The derivative of 36 is obviously 0. Do you understand that this is a problem? This is a problem not mathematically. Mathematically, it's there's nothing wrong with the operations, but it is a problem in reference to our application. How can I can I let me just be extremely blunt. Ready? If you've dazed off, if you're daydreaming, can you come back just for a second? Just come back just for a second and listen to me say this one thing. Don't substitute in until after you take the derivative. Now, I'm going to say that one more time. Don't sub, right? Don't sub until after the derivative. Okay. Now, the last thing I will address, and we are done with this problem, but the last thing that I will address is this negative symbol. So, in actuality, this is not the speed of the airplane. This is the velocity of the airplane. I know in normal day-to-day speech that most individuals interchange speed and velocity, but there is a difference between speed and velocity. Velocity has a direction. And in this case, the negative symbol is the component that represents the direction. But speed, here's how you can think about it. Speed is the absolute value of velocity. So the speed is 500 miles per hour. Now, if you would have, on a test, if you would have written negative 500 instead of 500, I would have written a note to the side about the correction, but I would have given you full credit because you've done amazing work so far, and I'm not going to discount that because maybe you had never taken a physics class. So at this stage, I'm going to go ahead and move to our last problem, and not that means that the video will be over in a second. That's definitely not the case, but it is the last problem that we're going to tackle from this handout. Ready? Here we go. So let me read. It says, find the rate of change in the angle of elevation of the camera shown in the following picture, 10 seconds after liftoff. Okay, so let me read. It says, a television camera at ground level is filming the liftoff of a rocket. Ready? So here is your camera. It's not safe enough to put a person there. So they have a camera installed, and this camera, what we want this camera to film the liftoff of the rocket as it rises vertically. Now, I don't know about you, but if you have any hopes of watching this on TV, then that camera, right, this camera right here, better begin to rotate as my apologies, as this rocket ascends vertically, right? So there better be some type of angle of rotation in that camera if we want to be able to watch this on TV. Now, to finish what I've been reading, so a television camera at ground level is filming the liftoff of a rocket that is rising vertically according to the position function. S is equal to 50 t squared. Sorry, that blowing was a little hair that got on my computer. So S is equal to 50 t squared. All right, now S in this problem is measured in feet. So hold on for a second. So let's do better than that. S is what? It's the height of the rocket. In feet. All right. T is seconds. So T is simply time in seconds. All right. So they also tell us the camera is 2,000 feet from the launch pad. All right, so what's nice is they drew us a diagram here, and it does, as you can see, it does appear that we're using a right triangle. So that's good, and we know the base of this right triangle is 2,000 feet. What other variables are in this problem? So that's where we got to go next. So, and at the same time, we're also asking, is that the equation that we're going to be taking the derivative of? Well, let's get back to the original question. It says, find the rate of change in the angle of elevation, right? So notice this theta symbol right here. Theta. So theta is the angle of elevation, right? The angle of the camera. Now, I'm not. It's the angle of elevation of the camera with respect to the ground is really what we have here. So now hold on for a second. So I'm looking at this position function, and I don't see any theta in there. So taking the derivative of that position function is not going to help me answer this, find the rate of change of theta. But it still may be helpful in the problem. So we'll have to see what else we can figure out. So if S is the height of the rocket and T is time in seconds, and it does appear that they tell us that T is equal to 10 seconds. So that would mean that, see if you can make sense of this. That would mean that if we just plug T in to this position function, we'll know this side of the triangle as well. Right? S, the vertical, the height. So let's go ahead and do that. So S is going to be equal to 50 multiplied by 10 squared. Right? So 10 squared is 100 times 50 is 5,000. So S is going to be equal to 5,000 feet. I'm going to write that. So 5,000. Okay, so that picture is a little bit cluttered. I'm going to try to draw it down here. So this is what we know about this right triangle. We know that the base is 2,000 feet. And we know that 10 seconds after liftoff, that rocket is 5,000 feet in the air. Now, do we know the hypotenuse? No. Could we figure it out? Yes. But let's see where we are in this problem. So maybe you're thinking, because I have to try to, without your eyes in front of me, I have to try to anticipate your questions. Maybe you're thinking, Professor, you said don't plug in until after you take the derivative. Well, that's true, but this guy right here is not the equation we need to take the derivative of. It was just simply an equation that we used to find one side of a triangle. So then what is the equation that we need to take the derivative of? Well, whatever it is, we're going to need to have theta in this equation, right? Because we want theta. So at this stage, let's see if you can, I'm going to clean up my mess down here. And let's see if you can agree with the following. So based on the triangle, I have two sides. What do I have? I have the opposite and I have the adjacent. So what is the function that relates opposite and adjacent? Well, I'm hoping your trigonometry is readily at hand. Tangent is how you relate opposite to adjacent. Now, what is the, well, we're going to go ahead and plug in. I understand that we turned S into 5,000. Stay with me. I understand that this was 5,000, but hold on. So tan of theta is equal to opposite over adjacent. What I want to do is I want to plug in the things that I know right now. So I know that tan of theta is going to be equal to, well, let's start with the adjacent. That's 2,000 feet. Now that's not ever going to change, right? That camera is 2,000 feet, no matter how much time goes by. But that numerator does change, right? It doesn't stay at 5,000. It's only 5,000 feet. The rocket's only 5,000 feet up in the air 10 seconds after liftoff. So we're going to leave this S, because that does change. Now, there we go. Now we have the relationship that we're looking for. S changes with time, theta changes with time. So if you take the derivative, and we are going to take the derivative of this, then I hope it makes sense that at some point in time, we're going to have if you take the derivative of theta, you're going to have a d theta dt. And if you take the derivative of S, you're going to have a ds dt. I'm going to go ahead and tell you what is d theta dt. Well, remember, it's a rate, right? It's the rate of change in the angle. And S, ds dt, well, it's obviously a rate of change. In what? Well, in height of the rocket. All right. So let's go ahead and take our derivative. We know that we know a little bit of information. We know t is equal to 10. And we know when t is equal to 10, S is equal to 5,000. Ready? Let's take the derivative. What is the derivative of tan theta? Well, of course, now I don't have a lot of room here, but this is d of dt. This is derivative with respect to time. So this is the derivative of tangent of theta is something that you can reference, right? This would be on a formula sheet. You can place these to memory. So many professors, I had many professors that make me place things like this to memory. It's a good practice in memory. I would not translate that into doing mathematics. I can do mathematics. I don't have the ability to place a whole bunch of trivia to memory. I can look that up, and as well as you can look that up when we need it. But the derivative of tangent, this is actually one that I do know. This is just secant squared theta. Now, if I took the derivative of a theta with respect to a t, then I do hope that you're thinking that you need a d theta dt. D theta dt. Okay. So now you want to take the derivative of the right side of this equation. Now, if I'm so sorry, I want to show you a little trick. Obviously, this is, you don't need a quotient rule here. Look, to divide by 2,000 is to multiply by 1 over 2,000, right? To divide by 2 is to multiply by a half. So S over 2,000 is the same thing as 1 over 2,000 times S, right? So now that's an easy derivative to take. if you take, so, right, if you take the derivative of 1/2 x, that's just 1/2. But if you take, so if you take the derivative of 1/2000th s, that's obviously going to be 1/2000. But since it's s with respect to t, we're going to need to have a ds dt. All right, now let's think about what we have and what we don't have. So looking at so what would we need here? So obviously the point of this problem is to find d theta dt, right? To find the rate of change in the angle theta with respect to time. But looking at the information that we have, somewhere in this problem, we must be able to find ds dt. Well, okay. So what is ds dt? What is ds dt? Well, first off, what is s? Well, obviously s is position. That would mean s prime is velocity. But what is s prime? Well, s prime is just the derivative of s with respect to time, right? Position function means that the position of an object has variation over time. And if you take the derivative of a position function, you would have a velocity function whose velocity varies over time. So in other words, ds dt is basically just the velocity. And we know how to find the velocity. All we have to do is take the derivative of s. So yes, I know that it's true that we didn't, I said we weren't going to be taking the derivative of that, but I meant for our solution of theta. So if s is equal to 50t squared, I need you to follow me. I know this is getting a little bit cluttered, but ds dt, right? That's s. That's the same thing as s prime. Well, the derivative of 50t squared would be 2 times 50 is 100 t. All right. So at this stage, I know what to place here for ds dt. So at this stage, I'm going to need to solve for d theta dt. So in one swoop, I hope this is okay. In one swoop, I'm going to divide both sides by secant. By secant squared. And I'm going to plug in 100t for ds dt. Ready? So let's see. So these would cancel, so that would leave me with d theta dt is equal to 1/2000th times, remember, ds dt is 100t. All of this over secant squared theta. Okay. Now I can go a little bit farther than this because I know that t is equal to 10. All right, so that's not bad. So we're getting somewhere. So that would mean d theta dt is going to be equal to, well, that's 100 times 10 is 1,000. So that's 1,000 over 2,000, so which is basically just a half. I'm going to write this like a student might, and then I'm going to reduce this. So it's been my experience that students are, well, if they have a decent training in trigonometry, normally they would say that they're good with sines, cosines, tangents. But almost every Calc 1 student that I've spoken with, they don't feel comfortable dealing with secants, cosecants, cotangents. So I'm going to fix that. So I need to, right now I'm going to box this in, and I need to erase so I can give myself some space here, okay? Okay, let me kind of write back some things that I just had. So this was ds dt. And I'm going to write, this was d theta dt is equal to, all right, well, this is 1/2, again, I'll keep it just like I had it, 1/2 secant squared theta. And now I can erase this. Now, I'm going to pause here. I'm going to pause, and I want you to think about this, right? Because this is not an easy problem. If you've listened to this video intently so far, I'm impressed, and seriously, hats off, because this is not easy. This is not an easy problem for most students. So, at this stage, what are you going to do? Right? Because you don't have a theta. Now, you could try to approximate theta, but let's think about it. If you're programming this, you're working for NASA, and you're and say you're the one programming these cameras so that they can, follow the rockets as they lift off into space. Listen, you don't want to play a game that if you're off by a few degrees or you're approximating your angles, maybe the people are watching a rocket and they can't even see the top of it, or they can't see the bottom of it. So we don't want to play the rounding game unless we have to, okay? So what are you going to do? Well, first, I can show you this. Let's see if you follow me here. This is, again, if you want to be an engineer, a lot of you want to be engineers. If you want to be an engineer, pay attention. Wake up, you need to be able to work things like this, right? It's not just, you don't go through engineering school just to take derivatives, like what's the derivative of x squared. Okay, that's not, I mean, we have software that can do all of that. That's easy. But right now is where we need someone with a brain that can think a little bit about what can we do. Well, let's see if we can make this a little bit easier. So look, d theta dt. Does it make sense? Does it make sense that to divide by secant is to multiply by cosine? I'll say that one more time. If you have to, go back to your trigonometry. 1 over secant is equal to cosine, right? So to divide by secant is to multiply by cosine. So I'm going to rewrite this. This is, we don't need to have this secant divide by secant squared. So to divide by secant squared is to multiply by cosine squared. So I can really just simply write this as 1/2 of cosine squared. All right, now we're getting somewhere. So what the heck is cosine? So cosine of theta is defined by its adjacent side divided by its hypotenuse, right? Cosine, it's a function. You give it a theta, it gives you back this ratio adjacent to the hypotenuse. So let's look at this triangle. Do we know adjacent? Well, yes, we do. This is adjacent. That's 2,000. That's easy. Do we know the hypotenuse? Well, not necessarily. We have to. Well, actually, I guess we're going to have to do a little bit of math to get to the hypotenuse, right? So let's think about that. So I know that I can plug in 2,000 here for adjacent. I need to know what should I plug in for the hypotenuse. Well, ready? That's where this 5,000 comes in handy. So remember, everything is dealing with 10 seconds after liftoff. So this is 5,000 feet. The opposite is 5,000. The adjacent is 2,000. Well, look, if I have two sides of a right triangle, I can figure out the third side. The third side, which is the hypotenuse, which is exactly what we want. The hypotenuse is going to be equal to the square root of 2,000 squared plus 5,000 squared. Ready? So what is cosine? Cosine is adjacent, which is 2,000, divided by the square root of 2,000 squared plus 5,000 squared. All right, that's great, except we don't have cosine, we have cosine squared. So we need to square that thing. So d theta dt is equal to 1/2 multiplied by, ready, here you go, 2,000 square roots of 2,000 squared plus 5,000 squared. And wait a minute, why am I about to put a 2 here? Because if this is, so if cosine of theta is the following fraction, then I don't have cosine, I have cosine squared. So I need to square that. So at least that radical is going to disappear. At this stage, we're going to let the calculator do some heavy lifting for us. This is going to end up being 1/2 times, again, you can always double check me. If you square everything, this is just going to be 4, and take away that radical, reduce, we should get 4/29. In other words, once you multiply these together and reduce, you should get 2/29. That is your answer. Does anybody know the units? That's a good question. So this would be, what? That's a rate, so it better be over seconds. And it's an angle, dealing with an angle, so it's radians per second. So what did we just do? Well, here's what we did. Here's a camera, and the camera wants to see the rocket, and the camera needs to rotate, right? This direction needs to rotate 229 radians per second if you want to keep it in the viewing lens throughout the entirety of the launch. I hope you stuck with me, but if not, I'll see you next time.